Good morning, folks. This is the first lecture of week number 2. So, on the agenda today, there is this item, which is chapter 4 from the book, and it concerns a rotating disk. Now, in doing this problem, I will do it multiple different ways. For example, I will look at surface slider and also try to avoid surface slider, instead using a user-defined restraint. So we'll get there when we get there. Now, here's the situation. You have a disk with the details given on the left corner. And this disk is rotating at a constant angular velocity about its axis. It's the type of problem that we used to do in the stress analysis course. However, it is not covered there anymore. It could be that somewhere in your machine design course that is done. I'm not sure. But anyway, what we like to know is the stress distribution in this problem. If this is going at a constant speed, I hope you realize that any sector that you take, for example, a 45-degree sector, a 30-degree sector, a 90-degree sector, any sector that you take, the sector next to it has exactly the same distribution of stress. Okay, that's why in this particular problem, if you take, for example, a 45-degree sector, in this case, or 30-degree sector, for example, this rectangular face that you see on the side and the rectangular face that you see on the side on the left, they're going to be planes of symmetry. Actually, this is called the cyclic symmetry, but it's okay. This is a fancy way of saying that this rectangle, after it deforms, obviously it deforms outward. After it deforms, it stays a planar rectangle. The size, of course, will change. The size, of course, will change because of the centrifugal force. The shape is going to look different. It's not going to be rectangle anymore. It's going to be perhaps a trapezoid. But the point is that it starts as a plane. It remains as a plane. And the same thing on the other side. Isn't that exactly what we mean by a roller condition on that face, or a surface slider on that face? The answer is yes. Another way of stating that is that any point on this rectangular face does not move in the direction perpendicular to that face. Think about it. That's the same thing as saying that things on that face are basically rollers. Okay. Now, of course, you can look at the solution, the stress in the coordinates x, y, z, true, but these three coordinates, namely the radial, the hoop stress means tangential, and the axial, are basically principal directions, and therefore the hoop stress, the radial stress, and the axial stress are principal stresses. Now, notice that the variation of the stress along the axial direction, say this is the z direction, along the z, is almost zero. For all practical purposes, it's zero. There is nothing that restrains this thing from, shrinking in the z direction. Okay, so this is because of the condition that we have for the problem. And radial and hoop, of course, they can be calculated from these formulas. Now, notice that there is density popping up here in addition to Young's modulus and Poisson ratio. Poisson ratio is there. Of course, Young's modulus is going to come into the deformation, not the displacement. It's not going to be in strains, for example. It's not going to be in stress formula. But the density is there because basically we have the centrifugal force. Remember mr omega squared from your physics class? There we are. M plays the role of M plays the the role of rho plays the role of m. This is density, mass density. Omega is omega, of course, and then r is, you look at this combination, it's going to pop up there. Okay. Now, the first thing I'm going to do is I'm going to model this thing as with 3 planes of symmetry. Notice that these were planes of symmetry. Also, if you cut halfway through the thickness of this, that is also a plane of symmetry. Okay, so there are 3 planes of symmetry here, and you've got you have a choice of either making that uh, that sector, okay, or making the whole disk and start cutting it with different planes. All right, so I'm going to make a 45-degree sector. How about that? Okay, and the thickness of this is 1, so I'm going to make this thickness actually half, because it's half of the thickness. So let's go to CATIA. You start a part file. There we are. Immediately save it. So file, save management, save as. On my desktop, I make a folder called rotating disk. Okay, and I'm going to make this part and put it there. Now, there are different ways of making this rotating disk. One is to take a sector like that and then pad it, a 45-degree sector like this, and then pad it. Or I can draw a rectangle and then shaft it. That's how I'm going to go. That's the route I'm going to take. Remember, these problems, these models, are many ways of doing it. So on that vertical plane, I will sketch a rectangle like that. This height is half the thickness of the disk, so that's 0.5. Okay. The dimension between this axis and that is, I believe it's 1. Yeah. And the outer radius is 6. So the dimension between this and that is 7. Oh no, I'm sorry, 6. Yeah. Excuse me, 6. All right. Exit, exit, right there, and then shaft it. Shaft it for 45 degrees. And for the axis of shafting, rotation, we're going to use this right there. And we say OK. Did I say 45? I can't remember. I'm not sure whether I typed 45 or not. Yeah, 45 degrees. Good. Now, I will come back and either draw a line right here at the axis of rotation, or I will do something else. Instead of a line, I'll do something else. We'll see. We'll see. So let's make this thing out of steel. So metal, scroll down steel on that part and say OK. You'll see why I will have to come back to this part design later on. So click on the floppy. OK. And then we're going to go to generative structure analysis and simulation. Generative structure analysis. CATIA sees a solid object. Immediately, it meshes it. Now, remember, we are doing a static analysis. Okay? Say OK. Now, I want to ask you a question. Where do you think the biggest stress is going to be? The critical area is going to be? Now, if you look at this formula, you can figure it out, but just using your intuition, it's going to be at the inside hole. So it is a good idea to make a finer grid at the inside face. And I'm going to do that. Now, first of all, let's go back to our analysis here. Let's see the mesh. There we are. By the way, this is parabolic. That's fine. I didn't say anything about the nature of the mesh, but that is parabolic. I'm just letting you know. Now, then we deactivate this mesh and do a local mesh refinement here. Now, remember, local mesh refinement is done in the model manager, second icon to the left, and right here, local mesh size. So you select that, and notice that based on what I did previously, it puts a number here. We can change this. We can make it smaller or bigger, whatever, and that size will change. So I'll just keep it like this. Now, if you want to see the mesh, right click, activate. Notice that over here, it's going to be a lot finer mesh. You can see that. You can see right here. Okay, good. This is the critical area. Now, deactivate this mesh again. Before we forget, let's go save an analysis. So file, save management, analysis, save as. In that same folder, which I call rotating this, you're going to save it as analysis 1. Okay, good. Now, we know I'm going to do this problem 2 different ways. One with surface slider and one without surface slider. When it comes to doing it with surface slider, I'm going to click on that. There's surface slider. And I'm going to click on the other side. I could have done it, by the way, in the same surface slider click. You know, this thing right now, one for there, one for there. If you look at it, there's 2 surface slider. I could have done both of them in the same place, but I'll do it like this. Good, good. Now, the question is, what is the load? Now, remember, this load is coming from centrifugal force. Centrifugal force is coming from basically radial acceleration. Go back to a dynamics class, okay? Go back to machine dynamics class. So because of the rotation, there is an acceleration towards the center of the disk, and therefore we're talking about acceleration. Now look at it here. There is the linear acceleration that we did a problem in the lab last week, and then there is the rotational force. Rotational force is coming from the radial acceleration. You click on it. It's a body force, so it doesn't matter what I pick. It's going to pick the whole thing. Okay. Now, as far as the rotation axis, I have a problem. The rotation axis is right here in there, but I cannot pick it because I don't have a line. I can't select this. I can go and select, for example, a line here, but this is wrong. It's not rotating about this line. It's rotating about a line here that unfortunately I don't have. So I cancel that. This is why I said I will have to go back to the part and create that line for myself. So here is how you go to the part. You expand the tree here. You expand the tree here. Double click on the part. You are in part design. You can see that. So if you want, you can go and create a line here, right, starting at 0, 0 in the vertical direction. However, I'm going to do it a different way. Notice that there is a toolbar down here, which says tools actually. And right there is the ability to create an access system. It says access system. See that? Access system right there. You click on it. What it does immediately, it creates an access system at the global origin right there. Now, if I don't want this origin, I can go and select some other point. I can put the access system there or there, etc. But I want it there because I want to use the axis Z as the axis of rotation. And by the way, there is this button current here that I'm going to uncheck because after I'm done, notice that when I uncheck that, this becomes dashed, okay? After I uncheck it, I don't want this coordinate system to be used for any other purpose. That's why I don't want to inadvertently, use this coordinate system for something else. So I unchecked it. Not a big deal in this problem. You can leave it the way it is. Now, let's go back to the analysis. Back to the analysis. Click on that rotational force. Select the support. Support is that whole body. Doesn't matter what you pick. It's a body force. It's going to take the whole body. And for the axis of rotation, notice that I can go and select this. Instead of creating a line, I created an axis system for here, and I'm going to use this axis Z. And notice the icon that it puts there, it's just like something rotating about that. Good. Now, the angular speed is 1000 RPM. What was it? I'm sorry. Let me see now. 1000 RPM. So what I can do is I can put 1,000 there. The unit here is RPM. That's fine. 1,000 RPM. Now, there is an angular acceleration here that we are assuming is 0 because it's going at a constant speed. Therefore, this is 0. We say OK. Very good. Oh, I forgot. The bottom of this thing is also surface slider. So I'm going to do either a third one or put it in there. No, I'll do a third one. So this bottom is also planar symmetry. Okay? Gradually, I'm going to go and remove these planes of symmetry for you as we go along the lecture. Save this thing. Okay, and I'm going to click on the compute, the calculator here, say OK, and just wait. Very good. Don't worry about this warning message about rotation not being a degree of freedom, etc. So that's fine, no problem. Unfortunately, you have to live with it. Now, let's look at the deformation. The deformation is that this, because the centrifugal force just radially moves out. Does it? Yep, yep, right there. You can see that. If the disk turns at a constant speed, this will stretch out. Okay, good. Now let's look at the displacement. You click on the displacement. Notice that every point moves out. If I want to see it in color, contour color, double click on this or double click in the tree. Every time you generate something is generated in this branch. Average ISO, say OK, and change the rendering. Good sign. Remember I said that the sector next to it will look exactly like that? You can see why, because these are all radial patterns, radial, circular contours. Okay, good. So the amount of deflection, of course, is very small because this is a 1-inch thick piece of steel, 1,000 RPM. Yeah, we don't expect a lot. This, by the way, is inches. If you can change these things, let me see now. It's up to you. You can go and change these things to millimeter, meter, whatever you want. Now let's look at the von Mises stress. There we are. Biggest stress in the middle, as you can see. But it's very low, actually. You can see that. This is not a gum. It's a piece of steel, 1-inch thick, going at 1,000 RPM, which is not a big deal. It's not going to, yield or something like that. Remember, your car engine, the idle is about, 700 RPM or something like that. Okay, it can go up to 3,000 RPM. It doesn't fall apart, right? Okay. By the way, notice that the colors are all mixed up here. In other words, it's not a smooth coloring if you want. If you want to change that, you can double click on the legend, go to the one with the three dots, and instead don't show it to me smooth. If you want, show it to me in bands. It's up to you, no big deal. Good. Now, what I want to do is I want to go and remove these surface sliders and instead put a constraint saying that nothing perpendicular to it. Okay. Now, let me deactivate this. And I'm going to delete all surface sliders. Good. Now, on this face, perpendicular to it is the direction X. So you go and click on the user-defined restraint. You see that? On that face, nothing moves in the direction X. Perpendicular to it. Look, perpendicular to it is X. Good. On the bottom face, nothing moves perpendicular to it. Now, perpendicular to it is in direction 3, direction Z. See that? Nothing moves perpendicular to it on that. My problem is going to be on this face because on purpose I took a 45-degree sector so that this normal to this is neither X nor Y and nor Z. In fact, it's a 45-degree to X and Z. So here's what you're going to do. Just like I created an axis system here, I'm going to create an axis system at one of these corners. at this corner, for example, and make sure that its x-axis is aligned that line so that we have a well-defined coordinate system. So here's what I mean. First of all, to create an axis system, you can't do it here. You have to go back to the part. Double-click on the part. Do you remember this toolbar? Remember the axis system here? You click on it. It says, where do you want to do it? Well, the origin, I want to select it to be this point. Do I want it like that? No, I want one of these axes, X, Y, or Z aligned with that line. For example, maybe I want X to align with that line. There, you see that? X is now along that line. Now, in this coordinate system, perpendicular to that face is Z. Okay? Just be aware of the fact that I decided to put X on this line. That's how it came out. So in that coordinate system, Z, perpendicular to that face is Z. So we say, okay, go back to our analysis. There we are. User defined. On that face that I had problem with, not this coordinate system, not the global one, the user one, the one that I created. It says, okay, tell me where it is. Well, this is the user one. And nothing moves in the direction Z. You see that? In that coordinate system that I selected, axis system 2, perpendicular to that face is actually direction Z, right there, which is direction 3. We say, okay. Notice that I don't have surface sliders anymore. We're going to run it, and we're going to get exactly the same answers. Look at the von Mises stress. Well, exactly, not quite exactly, almost the same answers, okay? And I bet if you did the displacement, you're going to be very close to what you had before. Basically, what I'm telling you is that surface slider or roller is nothing but a user-defined restraint that says no displacement perpendicular to that face. Okay, good. So now what I'm going to do is this. I want to repeat the same problem. And remember, you can use surface slider or you can use the coordinate system like they are. It's entirely up to you. If you don't like these, take them off, make them surface slider, all of them. Okay? But I'll leave it like this. Now, I want to go back and take away that bottom plane of symmetry, right? So let's go back to the part design. Let me go back to part design, and I was going to say, yeah. So let me change the rendering here. This thing makes me nervous. Okay. All right. Now there's two ways to eliminate this bottom plane of symmetry. One is either to go to the sketch. Remember the sketch? Remember I made this thing 0.5? You can make it 1. That's one way of doing it. Or you can say, you know what? Why don't I mirror this object with respect to this bottom plane? I can do that. Here is the mirror. Fine. Here is the mirror. Here is the mirror. It says, read the bottom left corner. See, bottom left corner. Bottom left corner of the screen. It says select. Oops. Select a plane or a face. This face. And what it does, it mirrors it. Very good. Go back to the analysis. First of all, this middle one should not be there because we don't have a middle plane of symmetry anymore. So I'm going to delete this. Gone. This one is okay. Nothing perpendicular to that. I bet this one is okay. Nothing perpendicular to that. Remember, we decided not to bring the surface slider. It would have been easier. We would not have to do this coordinate system, etc. But I decided to keep it the way it is. The problem is that when I run this, it'll bomb out. and you will see why in just a minute. Good. It says it could not finish it, it could not run it, and the reason, maybe if I plotted the deformation, maybe I can see it. Deformation, see that? It didn't finish, it didn't run, gave me an error message. But let me undo this thing. Okay, good. You might say, what happened to it? Okay, so let me look at the deformation. It actually moves the rigid body down. Now, I don't know where it is, but let's let me find out. Let me find out. One way to figure out, change the scale here. See that, the scale right there? There. And animate it. You see, it's moving as a rigid body. So, cancel that. Deactivate this plot. You have to prevent the motion at one corner point, up or down. Basically make it 0. Now, the reason it didn't have it with the third plane of symmetry is that we put it on a roller. It could not go up and down. But now I'm going to click on the user define on any corner point, this one, somewhere else. You just have to be a little bit careful here, because it is not in the direction, it's not the user, it's not in the user coordinate, it's in the global one. I want to make sure that it does not move up and down in the direction Z, direction 3, with the global coordinate system. If this was on a user, then you should say direction Y, because in the user coordinate system, up or down is Y. This is why I said you have to be a little bit careful when you use local coordinate system. Make sure that when you use it for a particular purpose that you have in mind, do not keep it active. Okay, so in the global coordinate system, I don't want this corner point to go up and down. Okay? All right? And just one more time, if this was on user, and I had selected this, it would actually be in this direction. So let me change the wireframe, see if I can show it to you. Current axis. If it was this, which is user, notice that it puts it in that direction, because this is direction Z for user. This is why I don't want it. I want it global in that direction. Take away the rigid body motion. We say okay, and we're going to run it. Good, done. Let's look at the von Mises stress. 239. If it's color bothering you, put it on material shading, right there. Same thing. All right. So let me remind you what we have done. We took a 45-degree sector. I did both with and without planar symmetry, and I used surface slider or no surface slider. So one more time, if deactivate this. If you want to use surface slider, no problem. Let me delete all of these. 1, 2, and 3. Delete this. Delete. Okay, good. So surface slider here. Surface slider on this side. I decided to do it all in one shot. Not the bottom, because the bottom is not planar symmetry anymore. And then user define in the global, with the global coordinates of a corner point, of selected top corner point. In the global coordinate system, it's direction 3, right? Good. Run it again. Fine. Run, done. Right click, activate, same numbers. So, yeah, you have choices of doing different things. Now, let's say I wanted to solve the same problem, except that I did not want to use these side planes of symmetry. Actually, I did not want to use any planes of symmetry. So let's go back to the part. Already we mirrored it so that this thickness is 1. This thickness is 1. And if I want the whole disk, I shaft it, but not by 45 degrees, but 360 degrees. There we are. Now, the reason we got that error message, it says, wait a minute, you created local coordinate system number 2, axis system number 2. Remember I selected this corner point? Remember I selected this corner point? I put the corner point of the disk at, let me see now, where? At this location, for example. That location is gone. It says, how do you expect me to put it on that location when the location is gone? No problem. Right click, delete that. That's all that error message said. I still need the first axis system because I want to make sure that it rotates about it. No problem. Okay. So, there is one other problem, and that is this axis. Let's go back here. Remember how I fixed a point and said don't go up or down? Remember that? It's right here. It says you took that point away. So how do you expect me to do that? So let me do the following. Let me delete this. Okay. Now, when I run this, I'll find out that it'll bomb out because this can move as a rigid body. You already know that. In fact, it can go up and down, and it can also go sideways. So that's fine. So let's go ahead and do that. Good. Couldn't do it. Now, here's the way I'm going to solve this problem. What I'm going to do is create a, now notice that on the test, we're going to ask you to all planes of symmetry. So it's a blessing in a sense, because in this problem, when you use 3 planes of symmetry, it was pretty much the easiest way you could have done it, okay? But let's hypothetically, we insisted on doing this thing. Now, there's several things you can do. One is to create the 1, 2, 3 rule. Remember 1, 2, 3 rule? Take away the rigid body motion. Remember that? The other one is try to use the isostatic instead of doing that. Try to use the isostatic restraint, the anchor. Click on it. Let's say OK. And let's run it now. See what happens now. Yeah. Now, this message that I'm going now, we have to read it carefully. The analysis surface slider it's complaining about this surface slider. Remember, it says that, hey, you took away my surface. What do you expect me to do? So let me delete this. Now let's run it. That's what it was complaining about. Let's see what happens. Good. Can I look at the stress distribution? What did you get? 239. Change the strengthening to material shading. Notice that notice that right there. I'm having a hell of a time trying to rotate this thing and moving, but that's because there's so many elements here and they're all parabolic. But look at the pattern. 239. Would you like to look at the displacement? There we are. Okay. Now, If you look at the displacement, it will look weird. Okay, I'll show you what. Double click on this, average ISO. The stress is going to be right, correct display. You saw that circular ring, but for uh, for uh, uh, the displacements, you're gonna have it will look weird. It's not rings anymore. Let me material shading. Is that right? Maybe I change this thing to average. I thought I did. It does, but for some reason it's not giving me the colors that I want. This is good. This is good. Okay, you know what? I'm gonna swallow my pride. It's actually froze on me. Come on, this froze on me. And what I was gonna do, because this kind of froze. I was gonna change the element from parabolic to linear so that I can at least move things around. But yeah, this froze. Anyway, uh, stresses came out to be correct. The pattern looked correct. The number came out, but the um, display of the displacement definitely these are not circular rings. Okay, so it's not displaying it for me correctly because it shows me the coordinate system. It for the display it uses x, y, z component of the stress, right? But the circular rings of displacement are not displacement in the x, y, z. It's the displacement in the radial direction. So not that this is wrong, it's just that I don't want to see the patterns of displacement as XYZ coordinates in XYZ coordinate system. I want to see it in R theta Z coordinate system. Okay, but as far as the stress, it didn't matter because the stress, when you use the von Mises stress, you calculate the von Mises stress, you can do it in terms of x, y, z, or you can do it in terms of principal coordinate systems, which is r, theta, and z. Nothing wrong there. All right, folks. So we'll stop. See you on Thursday.